Welcome back everybody, High Tech Lab here. In today's video we're going to be reviewing our battery test and measurement rack that we built to create a standard for all battery tests moving forward. Battery technology is always changing, so it was really important for us to build a rack that will withstand the test of time. For too long we've been using water heating elements, heat guns, and blow dryers to test battery capacity, and those methods have their own inaccuracies. With this lab-grade equipment, we can be certain that the results we get are accurate. Without further ado, let's take a look. Getting started, we are working on this rack that I showed you guys how I built in a previous video. We'll put a card in the top corner. If you haven't seen that, essentially we have a HP electronic load up here, a power supply here, data acquisition unit here, and that's currently selected to measure one of these cell voltages. And besides that, we have a couple other meters down here, a couple frequency counters, and you can see this one right here is reading 14.1 volts, and that's just off of these leads right here. They are clipped to some bus bars we have here down on either side of the battery. So these are positive and negative bus bars. Now, we do have some big 4-aught cables going between these bus bars and the actual batteries themselves. And these batteries right here are the NRAMP EA170 lithium iron phosphate prismatic cell. You can kind of see the label here a little bit. But either way, this is our system. And let's go around the back and I'll show you what all of these connections from the bus bars go to. Things are a little bit messy in here, but we have a 12 volt 3000 watt inverter charger down here. This is what we use for doing our bulk charging. And then coming up here, we have a Hewlett-Packard power supply, and that is what we do our fine charging with. And you can kind of see the voltage sense leads and that kind of thing here. And then coming up a little bit more, we have our electronic load. And here on the electronic load, we have a shunt. This is a 100 amp, 100 millivolt shunt. And that feeds into one of the cards here on the data acquisition unit. Let's pull one of those out and take a look at that. So this is the multiplexer card in the data acquisition unit. You can see we have multiple different channels and a couple extra terminals for 4-wire ohm sensing. This just slides into the back of the meter, and we have all of our wires coming out the back. And that goes in that slot right there and interfaces the meter. So this is how we do our data acquisition unit. And then we come out via a serial cable. That is this one right here. And I'll show you where we plug into our computer with that. I know it's a little bit hard to see because we have black on black here, but that is the USB cable going into my rack box. And that is the computer I use. Over here is where I do all my data analysis. Taking a look back at this electronic load, you'll take note that I have these channels in series. And the reason for that is these channels are only rated for 300 watts per channel, 0 to 60 volts, and 0 to 60 amps. So let's say we were running 60 amps at 60 volts. That would be way more power than this channel can handle. So we've seriesed them together so we can do up to a total of 600 watts. One channel we set on constant voltage, and the other channel we set on constant current. That way they're both doing half the work of a load on a battery or whatever we want to test. So here on the load we start up on channel 1. We're not drawing any voltage or amperage off channel 1 because there's nothing connected. Everything we have is connected onto channel 6 and 5. So I'm going to go to channel 5, and right now it's seeing 14.1 volts. Now, in order to get these channels to work perfectly in sync with each other, I'm going to set that at 6 volts for approximately half of the 12 volt battery we have connected. And then when I go to channel 6, it's seeing the remaining 8 volts because this battery is right about 14 volts. And then we would come here and set our current at 20 amps. And then when I hit enter, we can now see there's about 20 amps going through. Now this thing does have a little bit of a quirk. If you go back into current, it's set at exactly 20 amps. But if I go and look here, it's showing 20.05. So it doesn't give you exactly what you ask for every time. But I can use these input up and down buttons and dial it into exactly 20 amps. And now everything is happy. So I'm going to turn this input off. And now it says input off. And channel 5 is still on, but since current needs a loop to flow and that channel's off, that's why this channel isn't seeing any current. So with that being said, on this data acquisition unit, I have my shunt connected on to channel 16. Right now it's showing a couple of milliamps, microamps, however you want to guess which reading it is. But if I turn on this load and go back to channel 6 and dial back in that 20 amps, you can see now we're reading 20.11 amps, and I can slightly adjust the load and get it really close to 20 amps. So I've got 20.01 amps, and that's about as close as this load can get, but that's no big deal because this data acquisition unit will record all of that information. So this data acquisition unit is connected to the computer to RS-232. I'm going to briefly go over how we make that connection happen. So I'm going to hit Shift and then the interface button. Right now we're on RS-232. If you're using HPIB, you can select that there as well, but we're using RS-232 today. And change it here, we see 56,600 baud rate. We see no parity and 8-bit and no flow. And I haven't changed anything, but I'm taking note of those settings because that's going to apply when we get onto the computer. So first things first, we're going to open our device manager and check the properties for our serial converter. In our case, it's the prolific USB to serial COM port. And we're going to go into port settings and make sure all of this information matches what we just got out of the meter. In my case, my baud rate or bits per second started at 9600, and in our case, we need to change that to 57,600 to match what's in the meter. So we hit OK and then open Keysight Connection Assistant, and this is how it pops up. Now, it has already identified my piece of equipment here, the 34970A. So now we're good to go. And now we can open Bench Leak Data Logger. So now I'm in the Configure Instruments thing. I already went ahead and clicked New Configuration. I'll just go through this again so that you guys can watch the whole thing. I'll go Add Instruments and click Find. It's going to search all the buses, and in this case, it found the 34970A on serial port 3. So we're going to select that and click Connect. So now we can see on slot 1 on the back of the device, there's a 16-channel read multiplexer, which is correct. So now we can go ahead and configure channels. This is all set up for DC voltage, and that is not what we want. We want to set up only a few channels, the ones that we're using. So in our case, that's channels 1 through 4, as well as channel 16. So I'm going to set those to scan. Now, first things first, we're going to set the range so that it's not auto-ranging. In the case of our batteries, we're plus or minus 10 volts. So I'm going to set all those like so, and our resolution to 6.5 digits as well. Now for our voltage sensing, that is plenty good enough, but it gets a little bit interesting when it comes to our shunt for current sensing. On this one, we're going to set it to the 100 millivolt range. Still, again, the 6.5 digits of precision, but we're going to scale this by a factor of 1,000, and that's going to be amps DC. So with all this said and done, we are ready to go. So now when we go to the Scan and Log Data tab, I can set a scan time in here, and that scan time, when we hit the start button, it's going to start immediately. We're going to change it down to a 4-second scan time because that's a reasonable amount of time. Too fast and you put extra wear and tear on the read multiplexer. Too slow and you miss some of the important data. And we're going to stop scan by pressing the stop scan button. So with that said, when we hit the start button here, it's going to upload the configuration to the instrument and then begin scanning. So our data is going to come in here, and you can see each one of our cell voltages, which is pretty accurate right now, as well as the current on our shunt. Now take note, we told it this was in amps DC. It's smart enough to identify that it needs to be changed to milliamps DC at this range. But now I'm going to come over here and turn on the electronic load, and you'll be able to see immediately on the next scan, our current is up to 20.01 amps DC. Now I'm not trying to drain these batteries quite yet, so I'm going to turn the load back off, and you'll see this current in just a couple seconds drops back down. So we've collected 11 scans already in 44 seconds, so we can stop that. And we get a quick summary of some of the data. which we can then take a look at, has already been exported to a CSV file on our documents. Now, the nice part about these data acquisition units is that every single time you scan, it opens the file, writes the data to the file, and then closes the file. So if your computer were to crash, you don't actually lose any data, and there's also some internal memory on the data acquisition unit itself, so that if you're running a test, you can make sure every data point is saved, even if your computer crashes. With some of those extra cells pruned off, it is now easy to see our 4 cell voltages and the current on our load shunt. Now, we need to make a quick little formula, which is going to be, in my case, box K25, that represents at scan 7 the number of amps on the load shunt, and we are going to multiply that by 4 because the sample time was 4 seconds, and then we're going to divide by 3600 because there are 3600 seconds in an amp hour. So essentially what we're doing is we're converting 20 amps for 4 seconds into an amp hour. And in this case, what we get is a really precise number for amp hours. In this case, it's 0.022 and so on and so forth. So now Excel has actually applied this formula to the entire column for me, even though I only typed it into the one box. And we can go through all of our samples in this test and see, it's in all of the boxes. So now all we need to do is type in a formula for sum and select all of the amp hours that we have measured throughout the test. And from there, we can see in this test, we got 94.49 amp hours out of these batteries. So that's how you can use the data acquisition unit as well as the electronic load to do a test and get your amp hour readings. And we also have all of our cell voltages. So if we wanted to make a really nice graph for what the discharge curves were throughout the test, we have the ability to do that. One other nice thing about this data acquisition unit is it has an external trigger port, and that's just a simple DB9. And if we take a look back here, this electronic load also has a trigger input port. So we could quite easily automate the testing on this. We could have it set up so when that data acquisition unit sees 2.5 volts on a cell, for example, it's sending a trigger signal over here to this electronic load to shut down. That way we don't over discharge a battery. The other thing it has is HPIB on all of these pieces of equipment. You see that big old giant port on there? We could connect cables to all this equipment and have a network adapter that we don't have yet, but then all of these devices could talk together and we could really automate things very nicely by doing that. Well, that about concludes today's video. If you guys were inspired or have questions, be sure to leave a comment below. As always, thank you for watching. Be sure to hit the thumbs up, and if you're subscribed, be sure to double check that you have the bell icon turned on. Other than that, we'll see you guys in the next one. Bye now. Today's video was made possible by my business, Current Connected. Check out my website at www.currentconnected.com.